Frequency shifting is a method of producing inharmonic spectra by adding or subtracting a constant value to each of the partials of a harmonic spectrum. This preserves the differences between the frequencies but not the ratio, so they no longer create a harmonic series and thus a sense of pitch. Frequency shifting goes back to the days of analog electronic music studios. The first time that I heard about it was a device called the Klangumwandler, and there was also a module in the Buchla system. Ring modulation is a similar effect, except that ring modulation produces both the sum and difference frequencies at the same time. Neither of these things was used much because the signals put into them were usually just ordinary tones, and the result was a mess. Facts about frequency shifting. The frequency shifting value has to be added to or subtracted from the spectrum frequency. The value is usually described as a ratio or percentage of the fundamental, illustrating how frequency shifting works. Let's start by showing the math in computing frequency shifting. The way that it works is that the frequency shifted value is added to or subtracted from the partial. If we are using ratios, this would work as shown in the following examples. The first thing that we see is that shifting down produces negative values. Negative frequencies still have sound, but they cancel out positive frequencies. In the case of shifting down by 4 to 1, there is a plus and minus 1. In the case of 9 to 2, there are plus and minus 1 halves. Thus, the resulting amplitude of these partials will be the difference in amplitude between them. It will only be canceled out completely if they have the same value. Shifting down by a ratio of 4 to 1 produces the partials minus 3, minus 2, minus 1, 0, plus 1, etc., while shifting up by the same ratio produces 5, 6, 7, 8, 9, etc. These are still harmonic partials, but their positions change. Shifting down by a ratio of 9 to 2 produces minus 7 halves, minus 5 halves, minus 3 halves, minus 1 half, plus 1 half, etc., while shifting up produces 11 halves, 13 halves, 15 halves, 17 halves, 19 halves, etc. These are again harmonic partials of the tone an octave lower. Remember these facts. Harmonic partials are ratios. Frequencies are arithmetic. Pitch is logarithmic. Now let's look at the results of other values and the generalization that we can derive from them. In these examples, I will eliminate the partial number at the left side of the table. Here is a list of important facts about the procedure. 1. Simple ratios produce transpositions. Shifting by any whole number to 1 simply transposes the spectrum, but it remains harmonic. Some partials of the spectrum will be absent, but moved to another spot. Shifting to 2 transposes the pitch an octave down. Shifting by more complex ratios again transposes the pitch, but the fundamental may go into a subsonic range, anything lower than about 20 Hz, and there may be wide gaps between the partials. In the following charts, shifting down is in the left column and shifting up is in the right. Here we see that the fundamental in an n to 3 shift is 1/3 of the original frequency, 1/4 in n to 4, 1/5 in n to 5, and 1/7 in n to 7. Shifting by more complex ratios produces more interesting results. Shifting by ratios of 9 to 24, 11 to 24, 15 to 24, 19 to 24, or other complex ratios produces widely spaced frequencies with little apparent relationship to one another. 2. Pitch differences decrease as the spectrum increases. The greatest difference in pitch is always for the fundamental and decreases with each subsequent partial. When frequencies are shifted down, the pitch difference for the fundamental is more extreme, and on low notes that value can veer into the inaudible sub-audio range. The way to compute the frequency of any 12-tone equal-tempered pitch is to raise 2 to a power of something plus a fraction representing the number of semitones above C divided by 12. To compute A, 9 semitones above middle C, we raise 2 to the 8.75th power, which is 430.539. But the international standard is that A should be 440. So we multiply this by the magic number of 1.0219749. Let us consider the intonation of harmonic partials in relation to equal temperament, which is shown in the following chart. We can see that many overtones are pretty close to temperate intervals. Octaves are perfectly in tune, and perfect fifths and minor thirds are accurate within 2%. Major seconds are 4% sharp, minor seconds are 5% sharp, and major sixths are 6% sharp. Next in line would be major sevenths, 12% flat, and major thirds, 14% flat. After these, the overtones are considerably out of tune. The perfect fourth is 29% flat, minor seventh 31% flat. The tritone and minor sixth have really no good choices. 11 and 22 are 49% flat, and 23 is 28% sharp for the tritone. 13 and 26 are 41% sharp, and 25 is 27% flat for the minor sixth. Now let's look at what happens to the shifted partials. Suppose we shift the frequency of middle C up by a ratio of 2 to 5. Here are the results of doing this for some of the first 24 partials. From now on, I will show only a few selected partials. 8VE point PC form is a notation for pitches used in C-Sound and other programs. The integer portion represents the octave with 8 as middle C, and the first two digits represent the pitch clef, with 0.00 as C going up to 0.11 as B. Going higher than 0.11 puts you into the next octave. The third and fourth digits represent cents, or hundredths of a semitone. The chart shows the frequencies of both the harmonic and shifted partials. The pitch of the shifted fundamental is 5.83 semitones higher than the harmonic, and the second partial, an octave higher, is 3.16 semitones higher. The fourth, eighth, and 16th partials are similarly reduced to an amount of 1.65, 0.84, and 0.43 semitones. By the time we get to the 24th partial, it is only 0.31 semitones higher, and the 32nd is 0.22 semitones higher. Now let's see what happens when we shift down. The fundamental goes down 8.84 semitones. The octave partial 2 goes down 3.86, the fourth partial 1.82, and the 16th 0.44 semitones down, and the 24th is 0.27 semitones below. The problem with higher pitches is that the higher partials may go into the range of near inaudibility to humans. Here is what happens to a pitch 2 octaves higher, shifted up by a ratio of 2 to 5. The chart shows that the harmonic partials themselves are already stretching the limits of audibility. The 12th partial may be as high as we want to go with this tone to be heard by most humans. Thus, for higher notes, it is not possible to use the full harmonic spectrum. Here is what happens if we shift the same note down. The lower partials are shifted into a more comfortable range, but again it might be inadvisable to use a spectrum higher than the 12th partial. Now let us look at some different ratios. The next examples show shifting up by a ratio of 9 to 24. Now the fundamental is shifted up just 5.51 semitones, and partials 2, 4, 8, 16, and 24 are just 2.98, 1.55, 0.79, 0.4, and 0.09 semitones higher. Now let's shift down by a ratio of 9 to 24. Here the fundamental goes down by 8.14 semitones. The second, fourth, 8th, 16th, and 24th partials go down by 3.59, 1.7, 0.83, and 0.27 semitones. Now let us look at what happens to the note 5.00, C1, shifted down by a ratio of 9 to 24. The lowest frequency here, 20.44 Hz, might be inaudible, but the others are all fine. Thus, this note is too low to get all of the partials for this ratio. 3. Frequency shifting usually produces inharmonic spectra. Even though the frequencies shown in the previous examples are sometimes very close to their tempered components, They do not merge into a pitch with a timbre. However, some ratios do produce transpositions. When transpositions occur, the resulting partials are usually spread out in some fashion. In the example of shifting down by a ratio of 2 to 3 above, we get the frequency that is 1/3 of the original, represented by partials 1, 4, 7, 10, 13, etc. Example 1 plays a C2, 65.41 Hz, with its frequency shifted down by a ratio of 2 to 3. The frequency that is 1/3 of this note is 21.8 Hz, which is about equal to an F0 below the lowest note on a standard piano keyboard, but which exists on a Bösendorfer piano. It is probably not perceptible as a pitch, but you be the judge. Example 2 plays the same note shifted up by a ratio of 3 to 4. The fundamental would be 16.35 Hz, below the threshold of pitch, but the first partial sounding is the 7th or 114.61 Hz, so it and all the subsequent ones are audible. Example 3 plays the same pitch shifted up by a ratio of 2 to 7. Here the fundamental that would be 1/7 of the note is 9.34 Hz, which is way below the threshold of pitch perception, and the first shifted partial is the 9th or 84.09 Hz, and all the partials are so widely spaced that we don't get any sense of pitch. More complicated fractions result in more extreme results. Example 4 plays the same note shifted up by a ratio of 19 to 24. The supposed fundamental would be 2.75 Hz, but the first partial sounding is the 43rd, which is 117.19 Hz, and the next few are 182.59, 247.98, 313.41, 378.75, etc., which are all quite audible. The generalization to take away from these considerations is that transpositions will be evident only rarely, and the spectrum is usually widely spaced. How can we make use of spectra like these? Using frequency shifting. In order to hear the power of frequency shifting, we need to deal with the separate partials individually and slow them down so that we can hear how they relate to each other. While composers are used to specifying properties like dynamics, special modes of articulation, and other things, they are not accustomed to specifying the individual components of a sound. The values used in frequency shifting are usually described as a ratio with respect to the fundamental. Each ratio produces a unique set of spectral properties. When I think about using spectra in general, it gets back to the question of what is happening in the music. The music is constantly changing as notes enter and leave, creating different harmonies as it goes. Consider a harmony like a major triad, interval succession 0, 4, 7. The overtones series 1, 2, 3, 4, 5, 6, 8, 10, 12, 16, 20, and 24 would include just the overtones that state that harmony. Example 5 plays just these overtones of a harmonic series descending down from the 24th partial. We hear the harmonic series, which creates a timbre change with the pitch emerging towards the end of the tone. Example 6 does the same thing, but with the frequency shifted up by a ratio of 2 to 5. Here we hear a similar series of descending partials, but there is never a sense of pitch. The shifted frequencies get closer and closer to the harmonic overtones as they go higher. Here we hear something of the same effect, but not a pitch. While the harmony represented in this series of partials is not the same as the major triad, it does represent the way that the major triad is embodied in this particular frequency-shifted series. This analogy can be maintained with other harmonies as well, and it provides a reason for using different sequences of inharmonic partials. Also, as noted above, a series related by a 2:5 ratio can produce a fundamental 1/5 of the frequency employed. For the frequency of C1, 65.41 Hz, this would be 13.08 Hz, which would not be audible. For a note 2 octaves higher, C4, 261.63 Hz, the fundamental would be 53.33, which is a little bit sharper than an A-flat 1, 5.08 in 8VE.PC. This is clearly audible in example 7. Example 8 goes back to C1 with a ratio of 9:24. The fundamental would be 2.75 Hz, so it is clearly not audible, but the sequence resembles example 6. The difference between the partials is greater than example 7, but not as great as example 9, which uses a ratio of 19:24. While these examples do not have an audible pitch, a higher note could. Example 10 plays a C6, 1046.5 Hz, with a frequency shift of 19:24. 1/24 of this would be 43.6 Hz, just about an F1, 5.05. Since the components above 12 are too high, 13 is 14,433 and 24 is 25,945 Hz. This example uses all the partials from 12 to 1, and the lowest one is 1/875, a little higher than a B-flat, 10.10. The partials are so widely spaced that we hear no fundamental. Thus, we need to note that, in some cases, we may get a spurious fundamental with certain notes on middle to high range notes, but we usually get inharmonic spectra with frequency shifting. Now let us consider some other partial sequences and ways of presenting them. Example 11 presents an E1, 5.04, 41.2 Hz, with the partial sequence 24, 19, 18, 16, 12, 9, 8, 6, 4, 3, 2, and 1, and a shifting ratio of 19:24. Example 12 presents the same sequence on a G3, 7.07, 196 Hz, and a shifting ratio of 5:12. The contrast of these sounds is pretty extreme, even though it is the same partial sequence. From now on, the examples I will be playing are all taken from my composition Inharmonic Fantasy number 20. This work employs a frequency shifting ratio of 2:5 up. Another important fact about the piece is that partial sequences or portions of sequences are always stated from the top down. As with harmonic partials, different effects can be produced depending upon the number of partials employed for a single tone. One type of series which was illustrated above reinforces a specific harmony. Another type can reinforce different harmonies over the course of the duration. Example 13 plays an A1, 55 Hz, 5.09, with the series 21, 18, 16, 9, 8, 4, 2, and 1, which states the 0-2-5 harmony, followed by 24, 22, 19, 17, 12, 11, 6, and 3, which state a transposition of that harmony up a semitone. Example 14 is another sequence representing a transposition of a harmony. The note is A flat 1, 6.08, 103.83 Hz, and the harmony is 0-1-4. The partials 20, 17, 16, 10, 8, 5, 4, 2, and 1 state 0-1-4, and 22, 19, 18, 11, 9, and 24 state the transposition up 2 semitones. Now let's try some different sequences. Example 15 plays an E flat 2, 6.03, 77.78 Hz, with partials divided into 2 groups, 24, 19, 18, 16, 12, 9, 8, 6, 4, 3, 2, and 1, reinforce the harmony 0, 3, 4, 6, 7, and 23, 21, 18, 17, 15, 14, 13, 9, and 7 include all the remaining ones. Example 16 again divides the partials into 2 groups, but now they are attacked individually. The pitch is E flat 2, 6.03, 77.78 Hz. In the first group of partials, 24, 20, 19, 17, 16, 12, 10, 8, 6, 5, 4, 3, 2, and 1, reinforce the harmony 0, 3, 4, 6, 7. The second is 23, 22, 21, 18, 15, 14, 13, 11, 9, and 7, including all the ones left out of the first group. The next examples attack the inharmonic partials individually rather than fade them in. Example 17 plays the pitch B2, 6.11, 123.47 Hz, with the partials in 2 groups. 19, 18, 16, 9, 8, 4, 2, and 1 establish the harmony is 0-2-3, and 24, 22, 20, 12, 11, 10, 6, 5, and 3 represent T4 of 0-2-3. Example 18 plays an A flat, 5.08, 51.91 Hz, with the partials in 2 groups. 24, 21, 20, 16, 12, 10, 8, 6, 5, 4, 3, 2, and 1 establish the harmony as 0-4-5-7, and 34, 30, 28, 22, 17, 15, 14, 11, and 7 represent T6 of that harmony. Only 13 and 9 are not stated. Note that this uses partials 17, 28, and 34 in order to reinforce the transposition. Example 19 shows a more complicated harmonic sequence, the pentachord 0-1-4-6-9. The pitch is E flat 2, 6.03, 77.78 Hz, and the first partials are 27, 22, 20, 17, 16, 11, 10, 8, 5, 4, 2, and 1, which support that harmony, and the remaining ones 23, 21, 19, 18, 15, 14, 13, 12, 9, 7, 6, and 3 are put in at the end. Note that this uses partial 27 and skips 24. Now a definitely more complicated harmony, the hexachord 0, 1, 2, 5, 6, 9. The pitch is D1, 5.02, 36.71 Hertz, and the harmony is stated in the partials 24, 27, 23, 21, 18, 17, 16, 9, 8, 4, 2, and 1. This is followed by the remaining unused partials 22, 20, 19, 15, 14, 13, 12, 11, 10, 7, 6, 5, and 3. Now we double the speed of the partial attacks. Example 21 plays the pitch A2, 6.09, 110 Hertz, and the harmony is 013. The partial sequence begins with 19, 17, 16, 8, 4, 2, and 1, which reinforce 013, and the next group, 24, 21, 20, 12, 10, 6, 5, and 3, states T4. This is followed by the remaining ones, 23, 22, 18, 15, 14, 13, 11, 9, and 7. This entire sequence is stated twice. One more of these. Example 22 plays the pitch G2, 6.07, 98 Hertz, with the harmony 0, 3, 4, 5. The first series of 10 partials, 24, 21, 20, 19, 16, 10, 8, 5, 4, 2, and 1, reinforce this harmony, and the next 10, 26, 24, 22, 18, 13, 12, 11, 9, 6, and 3, state T2. The final 4, 17, 15, 14, and 7, fill in the remaining ones. This substitutes 26 for 23 to reinforce the transposition. Finally, let's add one more quality to these sounds, vibrato. Example 23 plays an A-flat 2, 5.08, 51.91 Hertz, with a harmony of 035. The partial sequence is 21, 19, 16, 8, 4, 2, and 1, supporting 035, and 22, 20, 17, 11, 10, and 5, supporting T1. The rest are 24, 23, 18, 15, 14, 13, 12, 9, 7, 6, and 3. There is a very slow vibrato that moves just one semitone up and back over the tone's duration. The last example, 24, is an octave higher A-flat 2, 6.08, 103.84 Hertz, with a 014 harmony, the same as example 14 above, except that it adds in the unused partials at the end. Now the vibrato is 3 semitones, slowly moving up and back over the tone's duration. Inharmonic Fantasy number 20. This presentation wouldn't be complete without a demonstration of all these ideas in action, and I offer my Inharmonic Fantasy number 20. The composition is in 14 sections, each lasting about 34 seconds. The tempo is 84 beats per minute, and the total duration is 8 minutes and 3 seconds. The entire piece is based on frequency-shifted overtone melodies and harmonies, as the above examples have shown. In order to allow high overtones to dominate the surface of the piece, only notes below C above middle C, spanning a 4-octave range from C1 to B4, are used. There are two instruments used, one fading and one attacking. The fading instrument brings the partials in and out one at a time, and the attacking one plays them individually. The piece begins with the fading instrument and transitions to the attacking instrument. At the climax of the piece, the instruments switch back to fading, preceding a subito piano. Different sections use a different number of notes per measure, and the octaves used are constantly changing. A couple of sections use vibrato of just 1 and 3 semitones, but these are quite noticeable. Different passages use different partial sequences. These usually state the harmony of the immediate context, the notes that appear in each measure. Some sequences use both the harmony and a transposition of the harmony, and some use all the partials up to a limit, usually the 24th. Sometimes the partial sequence is stated twice. There is one characteristic I have not mentioned yet, moving sounds. Normally, sounds are distributed more or less evenly around the listening space, but in this work they slowly begin to move in a circle around the room. The movement increases until the exact midpoint of the piece, when each sound makes a complete revolution from where it started and back, but this only works in the quad and octaphonic versions of the piece. In the stereo version, the movement only goes from one side to the other and back, so it is not as prominent a feature. Now you should listen to the piece and see if you can identify the ideas I've discussed here.